Hello again after the panel. My name is Maciej Świechowski, and I will be talking about supporting game design with evolutionary algorithms. This talk was submitted as an hour-long talk, but I got a half-an-hour slot, so I will be going quite quickly through this. So here I have 4 affiliations, but here on this talk I am representing QED Games, where we do AI for game development. So both tools for AI and just co-development of AI in your games, if you want. So evolutionary algorithms are quite old already. They were inspired by natural evolution by Charles Darwin, but the actual algorithms are already over 40 years old. So how it is that such an old technique is not that widely applied in game development? I will try to convince you that it's worthwhile applying them. So what's the main idea? The main idea is to use them to optimize basically any parameters in your game during the design. For example, how large a map should be in a strategy game, for example, or RPG game, anywhere where map is. There have been some use of them in shipped games, for example, Spore or No Man's Sky, but they were limited mostly to procedural generation before current generative AI. They were the old type of generative AI. There is even a book devoted to them. You probably don't know about it. It's very scientific, but I recommend it. It's Evolutionary Game Design by Cameron Brown. Okay, so maybe I will start with some summary, just to sell the idea, summarize what are the advantages and disadvantages of using evolutionary algorithm in game design. So the main advantages is that you can do it automatically. So you can optimize your parameters without human labor, and you can test lots of combinations of parameters. So you can explore the vast design space. And also, you can make this design driven by some numerical quality metrics. So it's more objective and it's more focused. But what are the disadvantages? You need to come up with a so-called fitness evaluation function. It is this quality metrics. Sometimes it's very hard to come by. Also, you need to make your game simulable. So you need to make repeated simulations from some starting point. And also they come with a huge computational cost. Okay, so before delving into applications, some basic terminology. Individual in evolutionary algorithms, it's a one candidate solution to this problem. So in terms of, like I said before, the idea is to optimize some parameters. So this can be the set of design parameters. The genotype is the encoding. So this is the numerical representation, the encoding genetic representation of this individual. And gene is one part, the fundamental unit of this encoding. Allele, it's the value the gene may take. For example, in classical genetic algorithms, it's bits 1 and 0, so allele can be 1 or 0. And phenotype is the materialization of these parameters of this encoding in the actual space. For example, here the genetic encoding can be some DNA sequence, and the phenotype would be the animal, for example. So the actual manifestation in the environment. And fitness is the quality of this individual. And the idea is to maintain a population of such candidate solutions, so a population of individuals which are manipulated by evolutionary operations such as crossover, which is like 2 parents meet together and exchange genetic information, mutation, which introduce some random elements. So it's different than crossover. And also selection, which represents the birth of a new population, new individuals. And the process goes in a loop until some condition is met. For example, we have an already good solution or some kind of number of iterations passed. But this is the basic idea. Mutation just introduces some random change to explore the space of the parameters, and crossover exchanges information. So maybe two good solutions will be even better, will produce even a better one. Okay, so that's the basic terminology. And now I will talk about one of the most difficult aspects, how to design a good fitness function, and also how to make the game simulable. So as I said, the fitness function assigns fitness, so the quality of a solution. So we have individuals and we have a game, and based on the performance of these individuals, we have to assign some values to these individuals. This is the role of the fitness function. And what are the types of fitness function? It can be deterministic, which means that, for example, we have some design parameters as a individual, and we can assign, based on them, we can assign the score, fitness score, so a quality of this individual, just based on them. Like every time, the same set of parameters will get the same score. So this is the deterministic example. There can also be non-deterministic when we, for example, need to do some simulations. We have to run the game multiple times and, for example, average the score, and there is some randomness in this procedure. And this is the non-deterministic way. And it also can also be direct. So based on the parameters, we can already tell how what the fitness is, or relative. For example, we need to make two sets of parameters fight against each other, and then assign the fitness. So it's not directly computable, and it's the best when the fitness function is deterministic and direct. So we need to run only once per set of parameters, but usually in practice it's non-deterministic and relative, unfortunately. It will be clear in a moment. And also, what does it mean that the game needs to be simulable? First of all, we need to distill some episodes of the game which look like this. We set the parameters which are stored in this individual and actually applied them in the game. And I will be showing some examples of these parameters. So I will be showing examples what they can encode, for example. But we need to set them in the game, run the game for some time to gather how they perform. Based on this performance, we need to calculate the fitness function, so how good these chosen parameters actually were. And then we need to make the same for the next individual, so for the next set of parameters. So we need to have also a mechanism to reset the state of the game to the same situation, some initial situation, and apply the new set of parameters. And in order for this to be feasible, it needs to be fast. This simulation part needs to be fast. So how fast it needs to be? First, let's take a look how long this process may take, this evolutionary algorithm optimization of parameters may take without any optimizations. So let's assume a common sense numbers, parameters, which are often work well in the literature. For example, 80 iterations of this algorithm, and in each, we don't care that much about the population size, so the number of individuals, the number of sets of parameters. we mostly care about how many new individuals need to be evaluated in each iteration, because this evaluation takes a form of a simulation in your game. So it takes time. The simulation is the longest. So let's assume that in each iteration, we have to perform 75 simulations, which is a common sense number. And let's assume that each simulation takes 40 minutes. So in such a case, this would take 167 days of CPU time. So we can already agree that it's a lot, considering that whenever the game changes, we need to probably rerun this. So it's too long. So how to make it feasible? So this is what I'm advocating also, how to make this algorithm just worth considering. There are 5 tips, 5 hints. First of all, for this, we usually do with headless build. So we skip graphics, rendering, maybe sound, animations, everything which is not needed to simulate this performance can be discarded. And by the way, to properly use this, we need to have AI bots, which I didn't say, that we make these simulations with bots, which are trying something in the game with the applied parameters from the individual. So any human input would make this very long, probably, because we would have to wait for humans. But since we use only AI bots, we can do headless build without graphics, without animations, without sound, just logic of the game. Also, we can increase the internal clock of the game. And in practice, it usually works up to 2 or 3 times, because then the physics will probably blow up. But this is usually feasible to make the game run 2 or 3 times faster, since it's already played by bots, not by humans. We, of course, need to implement the save and load system, so we can make it in portions. We can, for example, do some simulations in one day and resume the next one. And probably the most important thing to do is to parallelize the process. And evolutionary algorithms are extremely prone to parallel computing. Also, we can do some trick with caching fitness values, which I will show. Okay, so how to parallelize? There are 2 strategies. We can either just evaluate each set of parameters, so each individual on a different machine or a different thread, or we can maintain separate smaller populations and then combine them with some strategy. The simpler one would be the left one, so we just make each simulation run on a different thread. And also we can introduce the fitness storage. So even if our fitness calculation is non-deterministic, so each simulation can end up with different value, we can store these values, and until we have some enough number of them, so we have some statistical confidence about them, and when this number is hit, we can then only return the average value and do not simulate the same set of parameters anymore. So it's, from some point, it's instant evaluation. So given these optimizations, how long it might take now? So we didn't change the number of iterations, of course, but now, because of the caching fitness, I assume that the average number of calculations required per iteration is down to 40, and the average evaluation time is down to 20 minutes because of the faster clock and skipping the rendering. And finally, let's assume that we have 16 threads running in parallel. Now the computation time is down from 167 days just to 2.8 days. So I think it's acceptable. Of course, it depends on your production cycle. Okay, so now I will give some ideas of how this can be used. I actually had much more in-depth examples, but due to time limits, I can only present some of them, and in a shorter form. For example, we can optimize parameters of weapons in a first-person shooter game. So let's assume that the fitness calculation involves a battle or a series of battles, like head-to-head, between two bots. We have these bots, and we assume that the bots have the same logic, but they use different fixed weapons. And for example, for each pair of weapon, we can, by design, say, how do we want them to come up? For example, what's the expected win rate between those pairs of weapons should be? So this is our design constraint. And when we have this, it's easy to actually define the fitness function, which assumes the higher fitness, the closer the actual win rate achieved by this simulation is. And this way we can optimize the parameters of weapons according to our idea of how the win rates should be. So this is an example of a non-deterministic fitness function, because each match between two bots may end up being with a different score. But since we have a population and lots of repeats, it shouldn't be a big problem. With the same idea, for example, we can find the parameters of units in a real strategy game. So the game is fair. So the game is balanced. So here the encoding would be any number of parameters of units of each faction. So we can just, as one vector, store each HP points or abilities. For example, 0 if the ability is used, or 1 if it's the other way around. 0 if it's off, like it shouldn't be assigned to this unit, or 1 that the unit has access to this ability, and so on, like movement speed, like shooting value, some kind of attack value or armor, anything we have. We can encode them as a single vector, and then just make the game run. And each fitness involves battles between any combinations of factions. And in practice, we probably should just prepare a battle scenario with some units, some combinations of units, to make it not like play out the whole game. And based on the achieved results, we can, for example, compute the root mean squared error between the perfect win rates, so the perfect ties, the balanced game. And this is our fitness function. So the closer it is to this, the higher the fitness is. And for example, we can also use this for generation, like procedural generation. For example, map layouts for RPG games or roguelike games, or any types of games where there is some map that can be made from components, like unit bricks, for example. So let's assume we have predefined components, and we can encode the layout of a map in a vector. And for example, as a fitness function, we can define that we have some expected time to complete it by the bot, or for example, we can define it that we want the map to be as interesting as possible. So we want the bot to complete it in a higher time, but we don't want to be like unbeatable, so we set a limit after which the fitness goes down to 0. So it grows, grows, grows up till some limit and then goes to 0. And this, for example, can be a fitness function. So defining a fitness function requires some creativity, but it can be done. Yeah, in the same fashion, we can do fine-tuning of the shooting accuracy. So, for example, we can. It can be difficult to find a implement proper accuracy up front, because the game may be very dynamic, and so our accuracy value may not translate to actual hits because everything's moving and so on. So we can just do it empirically. So the encoding would be some shooting accuracy parameters of the bots, and then we test whether it's actually this in-game and assign fitness value again based on the deviation from this actual expected shooting, and then we can just fine-tune it. So maybe the set accuracy would be higher than the one we expect. Another examples, we can, for example, optimize tracks in racing games from predefined blocks. We can balance economy in games. We can optimize gravity parameter in a platformer game, for example, based on how long it takes for a bot to complete it or how many interesting events happened on the way. We can optimize the number of enemies to spawn in bullet hell games like Halls of Torment, for example, Vampire Survivors. Yeah. So we did a simple proof of concept in this area, and we had a like auto butler where there are 4 units controlled by AI, like smart units, and there are hordes of enemies, like dump units that attacks in waves in a simple like straightforward assault fashion. They just go the straightforward way to attack Grailbots. And there are 2 types of enemies, melee and ranged, and we wanted to make this game beatable, that Grailbots beat the enemies, but to make it interesting, we wanted them to beat it in a small possible margin. So the best example, the best case would be just 1 unit surviving with 1 HP. And this is a screenshot from this proof of concept. There are 4 units, and there are waves of enemies. And we tried to see whether evolutionary algorithms can optimize the parameters of those waves. So how many enemies should be spawned and what type, melee or ranged, how many melee enemies and how many ranged enemies. And we managed to do this. So this is the encoding. So also apart from the number of enemies in a wave, we also had the HP of each Grailbot. And we managed to do it using our engine in just this much code. I will just show how much code is required for this. So this is just setting the encoding, initializing the algorithm, then starting the evolutionary process, restarting the game, applying the parameters, and calculating the fitness function. And fitness function usually looks like this, that we have to calculate scores about. Here it's, like I said, we want the Grailbots to win, but with a small margin. So this is just not, I think it's not too much code. Yeah, and just to conclude, because I really had to fast forward this presentation, I want to sell you the idea that evolutionary algorithms can be used to optimize your game, but you have to specify modifiable parameters and fitness function, and you need to come up with a good fitness function, which can be difficult. You also need to have AI bots to play the game. So it must be played only with bots to make this whole idea feasible. And parallelization is really actually required for this. Yeah, and at this point, I have exactly 0 seconds. So thank you.